Utex Industries, and I'm here with Amanda Remlinger, our technical manager of our Weimar facility. And Amanda, would you like to go ahead and introduce yourself?
Yes, thank you for having me. I've been with Utex now for 8 years as of May. I actually graduated from Texas A&M University, Kingsville, so I am a Javelina. Go Javelinas. And I started out actually as a process engineer for the facility here. And shortly thereafter, I ended up responsible for the rubber department and mill room as well. So I've progressed from a process engineer to now being the technical manager of the facility here. So
we've had some previous discussions on rubber. So I wanted to elaborate a little bit more on our rubber to metal bonding process. So can you kind of go into detail about what makes a good part when it comes to the rubber to metal bonding?
Well, ideally, what you would want to have after testing, and most of what we do is going to have to be destructively testing, you would want to see rubber to rubber tear. So the weakest link should give first. So you'd want the material to actually tear, and you wouldn't want a separation occurring between the rubber and the metal. You would want your bond integrity to stay intact.
Is the bond a chemical reaction or a mechanical reaction?
The bond that we're obtaining here with adhesives would be more of a chemical reaction. These proprietary adhesives are actually engineered and specifically made to gear for bonding certain types of elastomers and metals. So the true attachment that is occurring is going to be a chemical reaction. It is not a mechanical attachment.
And so we're doing a chemical. What would be a mechanical?
A mechanical attachment could be a part that's been designed and made to basically hold the rubber in place. There are some mechanical attachments that occur based on the design of your part and how it could be encapsulated in your rubber. You may not at that time need any adhesive, and it would still basically be stuck on there. But that attachment is not a chemical attachment. It's basically just sitting on top of it and holding it in its place. So in something, in a part such as this, where your metal is actually on your OD, the shrinkage and pullback of your rubber works against you, versus if the elastomer was bonded and the metal was in the ID, you do have a combination of things occurring. The shrinkage and that mechanical pullback is helping and kind of lends itself to a more forgiving approach in bonding versus bonding something, to the ID where your rubber wants to pull away from that metal or your springs or whatever type of attachment that's occurring. But ideally, you want to have the chemical reaction so you have true rubber to rubber tear.
What about, are there certain compounds that bond better than others? And then, when it comes to the metal, is it the same thing? Are there certain metals that are going to be more forgiving than others?
In my experience, we have found simpler formulations, nitriles, HNBR seem to be a bit more forgiving. And then when you come to your metals, again, more simple chemistry, things like alloy steels, mild steels, we have found in general, as long as we follow, good safety practices, process safeties in place, we're able to obtain a consistent bond integrity for those types of items.
Okay. Now, are there certain compounds that are going to be like super difficult?
Oh, absolutely. One of the materials that we have the most fun with, I think, is as you get into materials that are more chemically inert, your fluoroelastomers, because of the way they're designed, they're meant not to, they're intended not to react, and we need it to react with the adhesive to get a true chemical bond. We do pride ourselves in our ability to do that, but it was definitely a learning experience for those. And in contrast to that, you have the flip with your metals as well, where metals, your simpler metals and things that are more common, you go into metals that are a bit more, I guess you would say, complex. Your corrosion resistant metals become a little bit more difficult to bond to. So we do preliminary screening when we have new metals, or we're working with new compounds. We use a variety of ASTM type of procedures to investigate initially and determine what's appropriate. But those are the ones we've had. Those have been more challenging, I guess you would say, than traditional and simpler formulations.
Right. So we might have touched on this earlier, but after bonding, how do you confirm that it's an acceptable part, before we ship it out to our customers? What do we have to do?
As I stated, we do preliminary screening on different types of ASTM standards and testing to validate. But in general, you're going to rely very heavily on the process controls that you have in place for these, because it's not just picking the right adhesive for your metal and rubber. There's a lot of additional things that have to occur, like your preparation of your metal. That can be varied. Your application method that's utilized for your adhesive can vary as well. And then you move to the actually molding operation and ensuring that things go, as you would want them to.
I know you have some samples there of different bonds. Would you be able to show us some of what you have?
Oh yeah, so this is an example. Here's two parts that we cut into. And I'm not sure how well it'll come up on our screen. We'll add some pictures later. But these are sample parts that we basically put on a saw, and then we sit here and we try and break at this bond interface to determine what type of failure we have. So this is a pretty common for us, the ASTM type of testing that we do. And so this is actually, the metal portion has been prepped, and then we bonded and applied this. We would input this into a fixture and use, in general, like an Instron or a Tinsel type of tester, and then basically start peeling back this rubber here, and then evaluate, once that's done, the degree of rubber to rubber tear that we observe after destructively, again, testing these.
There's different angles that we use, correct?
Yes, so in this particular case, we use a 45, and we actually peel, and there's different ways you can do it. We peel from the bottom up. So I'd like to think this is the most stringent and difficult test to pass, versus you can actually pull from up in this direction and peel and have it come up. The other thing is you have different fixtures that'll hold it, and here you can peel back and you put your Tinsel tester. And then, something like these are actually pulled, so they hold into your Tinsel tester and then actually pull in this direction. So you observe within here in these interfaces, the degree of error in each of those. And in general, the 45 and the peel up is the method that we use for our preliminary screening and efforts.
If you had a conversation with a customer and had one thing that you wanted them to remember about Utex, what would it be?
Initially, the industry started looking towards bonding perfluoros to different types of corrosion-resistant metals. We had to evaluate and do preliminary screening to determine, the best methods and approaches. And I think that we pride ourselves in our ability in an industry such as this to really push the boundaries of what others are doing. And I would say, for me, working for a company that's kind of on the leading edge of that, that's the most exciting part of working, for Utex.
Awesome, great. Well, Amanda, I really appreciate you taking the time to do this video for us today. Thanks again, and hope you have a great day.
Absolutely, thank you for having me.
Thanks for watching our video on rubber to metal bonding. If you'd like to learn more about Utex Industries, visit our website at www.utexind.com.